Hi. When studying field theory, we're going to want to study Lagrangians that have more than one field. After all, each particle is going to have an associated field. So if we want to study a system of multiple different types of particles, then we'll need a Lagrangian with different types of fields in it. So let's think about the simplest Lagrangian that we could write down with more than one field. So we'll take it up a notch. We'll just consider a Lagrangian with two fields. And what's something we could write down? Well, we have our Lagrangian. We're going to need some kinetic energy terms. And so we'll write the same type of kinetic energy terms that we were seeing before. Excuse me, that should be another phi1. So we'll call our first field phi1. Again, this is just going to be a scalar field, which is the simplest type of field that we can imagine. And this kinetic energy term, again, where does this come from? This comes from writing down a term which respects Lorentz symmetries, right? We want our Lagrangian to be something which is a Lorentz scalar, which therefore guarantees that it is explicitly respecting Lorentz symmetries as we want in our relativistic field theory. Okay, so we have some kinetic energy term associated with our phi1 field, which again you should have in the back of your mind. This is the excitations of this field might be associated with some type of particle. And then we'll want a kinetic energy term for our second type of fields, which I'll just call phi2. So these are just kinetic energy terms. We now want some potential terms. Again, the simplest terms we can write down are these phi squared terms. So we have minus 1/2 m phi1 squared. And then let's add a term for our phi2 particle. And this is one of the simplest Lagrangians we can, or maybe the simplest Lagrangian that we can write down, where we just have two scalar fields. We could make things more complicated by adding on terms that maybe have some constant and then have phi1 and phi2 both in that term. And these terms ultimately would be associated with interactions between phi1 and phi2 particles. But that complicates things. So we're gonna save that type of thing for a different day. I mean, this is okay, but complicated. I mean, I say complicated, but of course we're going to want our particles to interact with each other. But for the purpose of this video, let's just consider the simplest thing, where we have these two particles, and if we compute their Euler-Lagrange equations, we find, so we'll have an Euler-Lagrange equation for phi1 and separately an Euler-Lagrange equation for phi2. And if we just plug our Lagrangian into those equations, we end up with something that looks familiar. So this was just our same Klein-Gordon equation that we were seeing before, our same phi squared Euler-Lagrange equation that we saw before. Now we just have two of them, right? So this is where we're seeing it's the exact same differential equation, and we can solve it. And in this system, what we're seeing, this is what I mean by there's no interactions. Phi1 is just going to be doing its thing, evolving in time in the way it does. And whatever phi2 is doing is just going to be totally separate. And I noticed, sorry, there's a typo here. This should be a derivative. Sorry about that. Right, second derivative there. So phi1 and phi2 just don't even know about each other. They're both living in this space together, but because we didn't include any of these interaction terms that we could have, these guys aren't interacting with each other. They're two, it'd be like two neutral particles that don't know about each other in any way. This could not be an electron and a proton, which, an electron and a proton have an electromagnetic force between them, so they interact with each other. These are two things that would not interact with each other at all. So that's why it's the simplest. So this is a very symmetric Lagrangian. And again, that's partly because we didn't write down very many terms. We could write down things that would complicate this a lot. But as it is, it's very simple and very symmetric. And again, considering symmetries of Lagrangians is important for two separate and related reasons. So Noether's theorem teaches us that symmetries are associated with conservation principles. So that makes considering symmetries a very important thing to do. And also, just more generally speaking, whenever you have a symmetry, you should think of a symmetry as being something that you can exploit mathematically to make your life easier. Really, it just makes your life easier. So for instance, let's look at symmetries of L, of this Lagrangian. You know, a symmetry that's very explicit in this is we could say, instead of dealing with the field phi 1, let's consider a different field phi 1 tilde, which is just negative phi 1. If we go into the Lagrangian and replace all our phi 1s with phi 1 tildes, which is just the negative of phi 1, because you always, in every term, there's two phi 1s appearing, those negative signs are going to cancel each other out, and our Lagrangian won't change. And so we could, instead of dealing with the Lagrangian that's just phi, we could consider this phi tilde Lagrangian and mathematically, in this case, it doesn't see any mathematical savings, right? Because it doesn't change anything. Everything is exactly the same. And so we could, instead of talking about a particle associated with phi, there's this phi tilde particle, which would behave in exactly the same way as phi. Anyway, so here, I mean, okay. This is a very interesting thing to do, but it's true. The reason I mention this is just to get your brain sort of warmed up to thinking about other sort of more interesting transformations that we can make in order to study this Lagrangian or think about different ways of dealing with Lagrangians. So I made a typo on my Lagrangian. I wanted at first to consider the case where the masses of these guys are different. So sorry, in my Lagrangian above, I had just written m. I meant to write m1 and m2, which you noticed in my equations of motions. I allowed the masses of these guys to be different. Let's instead consider the Lagrangian where their masses have to be the same. So consider m1 equals m2 equals, I'll just call it m. So now we can write our Lagrangian as 1/2 d mu phi 1 d mu phi 1 plus 1/2 d mu phi 2 d mu phi 2 minus 1/2 m phi 1 plus phi 2. So this, because we've set the masses to be equal, we've actually introduced even more symmetry into our system. Now phi 1 and phi 2 are still, they're totally independent of each other. They still aren't interacting with each other in any sense, but now these two things, they're going to have the same mass. So we've introduced more symmetry into our system. Now we can do much more interesting things. And one thing we can do is we could consider defining sort of two new fields that are superpositions of phi 1 and phi 2. So consider phi A and phi B, where phi A is cosine theta, where theta is just some constant angle. So it could be 30 degrees, but here I want to leave it a variable to be as general as possible. But you're thinking of cosine theta as just being some constant number. It's some number, right? It's cosine of 30, it's cosine of 45, whatever you want it to be. but here I'm just leaving it general. But you think we're treating that as a constant. It's not like theta is a new field or something. So it's just some number times phi 1 plus sine of theta times phi 2. And then phi b will do minus sine of theta phi 1 plus cosine of theta phi 2. Where here, so these are quantum superpositions. So hopefully you've at least learned some about the idea of quantum superposition in your modern physics class, or certainly if you've taken a class in quantum mechanics, you should have learned about quantum superposition. And here, when I'm talking about superposing these fields, it is like a quantum superposition. And here in particular, we would call this is called a field rotation. I'm sort of rotating between phi 1 and phi 2. And I'm just defining this new field, which is a quantum superposition of my two original fields. And if you take these, if you solve, so first you'd have to solve for phi 1 and phi 2, and then plug these into our Lagrangian and do just some algebra, then you would find your new Lagrangian is not so new. It's the exact same thing that we had before. But now we have phi A and phi B. So this is a new Lagrangian that has exactly the same form as the previous Lagrangian that we had. And so if we solve for the equations of motion, the equations of motion of phi A are exactly the same, and phi A and phi B, these are exactly the same equations of motions that we had for phi 1 and phi 2. And so you start to wonder, what's the difference between like we know phi 1 is associated with some particle, phi 2 some different particle, and now phi A and phi B are they different, totally different particles? But somehow they're related to phi 1 and phi 2. Well, they are. You can really think of these. The phi A, the particle associated with phi A is like some quantum superposition of particles phi 1 and phi 2, which is a weird thing to think about because you're like, because don't we in the standard model just have some list of particles? We've saw that we have electrons and positrons and neutrinos, and there's this specific list. But now I'm telling you that there's not just that one list. We could instead find these sort of quantum superpositions of fields associated with those particles, and we could talk about sort of a different list of particles that maybe are quantum superpositions of those original particles. And that other list, in some sense, is just as real in terms of science. It's just as good. Maybe not just as good, it's going to be different. It's going to be different. And which particles you sort of think about, sometimes it's just going to depend. I mean, really going back and forth between these often you'll do to make your life easier, to make the math easier for some reason. And it's just going to depend on the particle or the problem that you're solving. Okay, so this is something that we can do, and this is actually reflecting a type of symmetry of our Lagrangian. So that's sort of helpful. Another superposition that we can find or that we can study that's going to be very useful is one which is complex. So here I want to talk about complex fields so again, I'm taking a quantum superposition of my phi 1 and phi 2. But now you're seeing this complex number show up. This is I, the imaginary number I. And so now we think of this field as something that doesn't just assign a number at each point in space-time. Instead, it assigns a complex number at each point in space-time. So this is sort of like one field, but it's also sort of like two fields, because at each point, rather than having a single scalar number, there's a number which is complex. So there's a real part of that and an imaginary part of that. So again, we should think of complex numbers. A single complex number always carries two numbers with it, right? It's two pieces of information. So in a way, this is one field, but it's also sort of two fields, because there's two numbers at each point in space-time. If you, again, find the Lagrangian that would be associated with this, then we can write it in terms of the complex conjugate of phi. And we can find the Euler-Lagrange equations. And we see they're the same as before. d mu phi star plus m squared phi star, and then 1 for phi. Where if you go through this calculation, and I encourage you to do that, note that you treat phi and phi star like they're different things. We know that phi star is actually the complex conjugate of phi, so we know that they are related, but you want to treat them as separate. And part of the reason for that is, again, because a complex field is carrying two pieces of information with it. We know that phi came from phi 1 and phi 2. We started with two different fields and we just defined it. So we still should always, this is always still just sort of like two different fields. But phi is sort of just one field. It's one complex field. So here, allowing us to have a complex field allows us to solve for both fields at the same time. And again, this was only okay, and things only work out this well because phi 1 and phi 2 had the same mass. And ultimately, studying complex fields is going to allow us, so when you should think of things with the same mass, what particles have the same mass? Well, a particle and its antiparticle. Those two things always have the same mass. And so when we study particles and their antiparticles, this really comes out of thinking about complex fields where you have the field and its complex conjugate. So complex fields are going to be very important. Now, we could do everything without introducing complex numbers. This is in no way necessary for studying these things, but it is going to make things a lot easier. So even though, again, we're making things mathematically maybe more challenging at first, there's a good reason for it. And it also, right, an electron and a positron should be related. You might wonder, like, why do these antiparticles, why is it just that we're changing them, the charge? Why do they have the same mass? Well, now, if we think about them as sort of the complex conjugates of each other, okay, well, then they have some deeper relationship. So this helps us to a little bit think of why. Why are they related in that way? All right, so that's a little bit about dealing with the Lagrangians with more than one field, and in particular, combining those fields into one as a complex fields.